and welcome back to PyCon AU 2024. Up next, we will have Mr. Dan Draper speaking. Again, PyCon AU 2024 is really excited to have CipherStash come and sponsor the commencing of this event, of which Mr. Draper here is the CEO of. So I'm sure everybody will be able to learn something from his presentation. And without further ado, I shall pass the mic to him. Oh wait, he already has a mic. Never mind.
Hopefully this works. You can all hear me? Cool. Thank you very much. Cool. So today I'm going to talk about fast, highly effective database security using this idea of searchable encryption, but there's going to be so much more. In fact, I think I may have packed too much into my slides, but we'll see how we go. So let's start at the very beginning. What happens to data after a form is submitted on a web browser or on a mobile device? First thing that's going to happen is we'll probably send a client request to a backend server, a Flask server or maybe a Ruby on Rails server, for example. JSON payload, nothing fancy there. Then what happens after we've processed this data in our application, we're going to save it into a database. PostgreSQL, maybe MongoDB. But we've missed something really, really important. And that is, how do we authorize ourselves? How do we know that the value that the browser is sending to the application is from a trusted source, that we can reason about whether or not we should process it? And the most common way to do that is using this idea of a JWT, or JSON Web Token. Some authentication service like Auth0 or Okta has, we've done an exchange with their APIs to get a JWT. We're going to include it in our request, usually via such a header like an authorization header, a bearer token, as you might say. But then when the application receives it, it's going to verify it. It's going to verify that that token was signed or minted, sometimes as we say, by a trusted party. So we trust that message coming from the browser. And then finally, the application is going to store that information in the database. But once again, the application needs to authenticate to the database. So it's going to do that via some query string, usually some pre-shared key or a secret. The response is very similar. So now we've done an insert. We want to do a query. It looks almost identical, except now we're going to return the results back to the browser. OK, cool. Hopefully this is not new information to anybody here, but we're all starting from a shared place of understanding. OK, so how do we protect this data? And what are we protecting from? So one way to think about it is in terms of sort of a policy system. So who can do what, when, or where? And the more formal way to think about this is the idea of a principal. So the principal is the user, but it might also be a machine. What action can they take, and in what context? And so I'll fire off some quick examples for you. So Jane might be the principal. She's allowed to create a user, but only within her company. So long as that user is attached to her company record, she can do that. John is allowed to read users, but say only between the hours of 9 and 5. That's not a policy we see very often. I argue that we probably should use policies like that more often. One of the reasons we don't is because it's difficult to achieve. Sachin is allowed to delete users, but only if his operating system is up to date. This is the idea of contextual policies. So I can log in and I can get a JWT, but only if I can prove to the identity service that my system has been patched or has the latest operating system and so forth. One common way to achieve this idea of role-based access control is using a package called Flask Authorize. So if you've got a Flask application, you could use these decorators to say, OK, in order to create a patient, you have to be logged in, and you have to have been granted the permission to create a patient. Cool, that works quite well. Similarly, on the read side, you could say, all right, so you have to be logged in order to get a patient, but you also now have to check whether or not you've been granted the read patient permission. But what happens if you forget to call that code? You miss that step. Unfortunately, it happens very often. So often, in fact, that the OWASP top 10, which lists the most common occurrences of security issues, or common reasons for security issues, lists broken access control as the #1. That was then the 2021 release of these issues. So it happens often enough. So what about row-level security in the database? Hands up who's heard of row-level security in a database? About half or a little over half. Cool. So we could look at doing that, right? So let's say we've got this patients table in our database, and we know that we've got a users table, and say our identity provider is auth0, so we don't store passwords, but we relate it to an ID in auth0. Then we've got some groups, and then we've got group members. Then we can go and create a policy. But wait, this is all dependent on how our application connects to our database. And remember that it connects via this pre-shared key, app, and a password. So that means the current user is always going to be app. We can't differentiate between the users. These JWTs that we're doing in the application layer don't mean anything to our database. So we can put row-level security in place, but everyone gets the same policies anyway. So why are we going through this pain? So row-level security in a database doesn't actually solve this problem for us. Okay, so I'm a cryptography guy. What about encryption? Well, SQL Alchemy has an option for that too. So you can use the string encrypted type, for example, and this is our patient model, and we might want to encrypt the name and the date of birth of a patient. Cool, that makes sense, but it's a bad idea. I don't recommend doing this. Sounds weird coming from me, being the encryption guy, but let me explain. The problem is this guy. It's broken because of this guy. Actually, no, by this, what I really mean is this. And by what I mean by this is this. Padding Oracle on downgraded encryption. And actually, don't worry, we're not going to go through this now. But the padding Oracle problem, we're talking about in the tutorial on Monday, if you're lucky enough to come along to that, is because of what's called a mode of operation with encryption. So if somebody says to you, oh, we use AES encryption, 256-bit keys or what have you, that doesn't mean anything to me. What's more important to me is what is the mode of operation that you're using AES in? And the standard way of doing it using SQL Alchemy uses this idea of cipher block chaining. And cipher block chaining has been around for years, decades actually. It's very simple, but it's totally broken. And in fact, on Monday, for those that are coming along to the tutorial, I'm going to show you how to fully recover the data without knowing the encryption key by exploiting this idea of a poodle, padding Oracle attack. So yeah, what we want to do is use a different mode. And so a more contemporary mode, much more secure mode is this idea of GCM. You don't need to know the details of this so much as just to know that the mode is important and that you should be avoiding CBC mode. If you're ever doing encryption, always make sure to use GCM mode. GCM mode stands for Galois counter mode, if you're interested. I'm going to fire through this pretty quickly, so don't worry too much if you don't follow it all. There's one really important takeaway that I want you to think about at the end. So very quickly, though, the way that GCM mode works is called an authenticating encryption mode. So we're going to take some random initialization vector, some plain text, just the unencrypted value, love coffee, and I'm going to take a 32-byte key. I'm going to put that into my encryption function, E, and I'm going to get out a ciphertext. So we call it plain text and ciphertext, the encrypted and unencrypted versions. And we're also going to get this thing called a tag. So the tag is proving that the information is correct. We can't tamper with it. It provides a level of authenticity. And the tag is very useful because I now need to provide that tag at the time of decryption in order for the decryption to succeed. And if the tag is incorrect, then I can't proceed. That goes one step further by using this idea of authenticated associated data. It's essentially taking some additional non-sensitive data, in this case just a information string, SSN, or social security number, for example, and proving that that information string is authentic and is always available when I'm trying to do decryption. So that way, if I try to decrypt and I don't provide the correct associated data, then the decryption will fail. So this idea of authenticated data makes our encryption contextual. And this is how we're able to use encryption a little bit later on as the context part of that principal action context policy framework I mentioned earlier. So some examples of context that you might include in your encryption are things like column name in a table, in a database, the individual row ID or record ID, or even information associated with the data when it was first captured, so the identity of the person who created the record, for example. But even ignoring poodles, how does encryption solve access control? It doesn't much. But let me explain. So what we actually want is encryption as access control. So encryption on its own doesn't necessarily solve the problem, but we can go one step further. So to make encryption useful as an access control mechanism, we need to do a few things. Number one is we need a key server. So rather than having a single key stored in our application or in an environment variable or something like that, we need a more intelligent service. Ideally, we want to have a unique key for every value. So not one key that's used to encrypt everything. We want to be able to derive keys based on the identity of the principal. So that is the user or the machine that's making the request. And the last piece, most important piece, it has to be searchable. We'll explain all of these parts. So let's talk about a key server very quickly. So a key server is a way to retrieve a key for a given encryption operation or a decryption operation. So a client, your application, for example, may request a key to the key server. Key server is going to generate a random key and return that as called a data key or a data encryption key sometimes. It's also going to use this idea of a root key that it stores within its own system to encrypt that data key and return it as an encrypted data key. So you now have two copies of the key, one encrypted and one not. And we're going to use the unencrypted key, the data key, to encrypt our plaintext, our message. So in this case, an email address, for example. We're going to store that value, that ciphertext. And then we're also going to store the encrypted data key that we received from the key server. We're going to store these two things together in our database. And so it's going to look like that. So you're going to get unique values for every field, and you're going to have the encrypted value version of the message or the email or name, along with the randomly generated encrypted data key from the key server. So when we want to decrypt, we're going to retrieve the original data key by sending that encrypted data key back to the key server. The key server is going to use its root key to decrypt that encrypted data key and send back the original data key. And we're going to use that decrypted data key to decrypt our original message. So it's sort of the chain of events that you need to follow. With me so far? Hopefully you're following that. And by the way, this root key in most key services is actually stored in what's called a hardware security module, or HSM. And so the big companies like Thales sell those products. They have all the letters. So just remember that they have the letters. Cool. So the other cool thing about a key server is that it's identity-based. So you can use this JWT that we got from Auth0 or Okta previously to determine, and the key server is going to use that to determine whether or not it will give you a data key. So we're getting a little bit closer to an access management system here now. Because what it can do is determine, based on your identity, any scopes that you might have in your JWT, and also this idea of authenticated associated data, AAD. Is it stored in the right table? Is it stored in a particular table? Is it a certain row ID? Was it created by a certain person? The key server can now make a bunch of decisions based on that information as to whether or not it will allow you to have a data key and thus decrypt and access the data. So a key server with a key per value derived based on identity. What about Amazon's key management service? That sounds pretty good, yeah? No. So we started out at SafeStash, we started out using AWS KMS and still do for a bunch of stuff. But when it comes to the database, it has some pretty major drawbacks. Number one is performance. So because we want to use it as access control, every value has to have a unique key. So that means that when we're performing decryptions, the way that Amazon's KMS works is you've got to send a request, a network request to KMS for every single decryption. So if you've got 3 rows of records, 2 columns, you've now got to make 6 separate requests to KMS. and it absolutely kills performance. Frankly, KMS was never designed for this use case. And so what Amazon ended up doing was they created this idea of data key caching. So instead of using a key for every record or every value, you use it for a bunch of records. And so one way to think of that is if you're inserting a bunch of information into a table, a bunch of records, you might change or expire that data key cache every so many records. So in this example, I'm using it for 8 encryptions. So we're going to insert 8 records and then rotate and get another key. Then you're going to do another 8 records and then another 8 records. So that's fine, except first problem is we now don't have a way to uniquely identify those values. So our policy system becomes a little weak. In fact, in a lot of cases, we wouldn't be able to use that idea of encryption as access control. But there's actually a bigger problem. Even though this solves the performance problem during insertion, it actually doesn't solve it for queries, because the way the access patterns for your data at insert time are often different to how they are at retrieval time. It's a random access problem. So I might send a query to the database where I'm saying, in this example, select email and name from the users table where type is merchant. Now that's not going to get records that happen to have been inserted together. They're going to be randomly retrieved. And so in this case, we're back to the same problem before, where we're now having to make multiple requests to KMS. We battled with this for a long time at SafeStash before we finally gave in and created our own key management service. We call it Zero KMS. It supports batch operations. It was designed from the get-go for database encryption. It runs anywhere, so it can run in any cloud or even on-prem, and it's significantly faster than Amazon's KMS. The first version was 9 times faster, and the new version, which is coming soon, should be up to 500 times faster. For a whole bunch of reasons, I could probably do a whole talk on that, but Zero KMS is a really important part of our offering. Dan, when are you going to talk about searchable encryption? That's what we're here for, right? Well, okay, let's talk about searchable encryption stuffs. So remember that with this idea of encryption as access control, we've just inserted a bunch of encrypted values into a database. Now, these queries will no longer work. Let's say I want to look up some condition where the user's email is some value. Or range queries, so where the date of birth is more than 1st of January 2000. Or if I want to order, just sort by people's names. In fact, that second query here will run, but you'll end up with random ordering, so it doesn't mean anything. And certainly things like fuzzy and partial text matches are totally out of the question when it comes to encrypted values. So to solve these problems, we need to look at something called searchable encryption. And so there's a whole bunch of different technologies available and that we use, and in fact MongoDB has some searchable encryption too. I met the guy that wrote that code. But in SafeStash, we've got a couple of particular what we call primitives that we use. And so the first is called order revealing encryption. And to give a sense of how this works, it's first helpful to think about what it looks like before we encrypt when we're doing some sort of range comparison, right? So if you've got two numbers, 200 and 100, and you want to compare them, you'll get some result out. If 200 is more than 100, then we're going to return 1. If 200 is less than 100, we're going to return -1. And if they're equal, we're going to return 0. So this is like just a standard comparison operation. See it in many languages. In an encrypted setting, what we're going to do is use this special kind of encryption function called an ORE encrypt function. And that's going to output some ciphertext. And then we're going to do the same with the other value. And now we have a ORE comparison function which takes these two encrypted values and outputs only whether or not they are equal, more than, or less than. And so it reveals their order, but nothing else. We don't actually know what those values are, we just know how they compare to each other. So hence order revealing encryption. Another example is how we might achieve fuzzy text queries. And so we can use this idea of encrypted Bloom filters, and once again, don't worry too much about how this all fits together, just know that it's possible. And a very simple intuition for this, it's slightly more complicated than this, but to give you a sense of how it works, I'm going to take some value, some query term, say my name. going to split it up into what we call n-grams, in this case trigrams. So these are chunks of the input text of 3 characters long. So Dan, ignoring the space, Anne, DRA, RAP, and so forth. And then for each of those terms, I'm going to put it through this Bloom filter encryption function, and it's going to pop out a bunch of seemingly random numbers. And actually, seemingly random is a really important concept here, because to an attacker, to an observer, it is indistinguishable from random. They can't tell the difference between random numbers and this. But if we happen to know the key, we can generate a query which might look like this. Let's say that I wanted to do a partial text search. So I'm now comparing DRAP, see if it matches Dan Draper. And so I'm going to end up with a smaller encrypted Bloom filter. And I'm going to compare simply by checking to see whether this second array of values is contained within the first array of values. That's a simplification, but it gives you an intuition of how the process works. So that's telling me whether or not this string is contained within this string, and doing so in an encrypted setting. Okay, so what about SQL? I use SQL, not OREs and Bloomy Watsits. Well, that's why we created EQL. So EQL is encrypted query language. So if you're interested, I wasn't going to go through this today because I didn't want to make it seem like we were trying to pitch you, but if you're interested in exploring this a little bit further, you can check out our repos. So EQL is effectively a way to make SQL encryption aware. And so if you can do it just in plain SQL, or you can use EqualPy. We've been debating all week how to pronounce EqualPy, EQLPy. I like EqualPy. And it's our Python library for encrypt query language, which we made available this week. So if you want to check that out, you can do so at Sifestash, on our GitHub at sifestash/eql-py. A couple of things that EQL can do. One of them is this idea of setting the identity. So if we go back to the beginning, when we had this idea of the database only knows about the app, it doesn't know who you are. One of the things that EQL is intended to solve is we can pass the JWT from your application all the way down into the database. We do that using this set identity command. And so that is telling EQL who the user is, effectively through their JWT, and so we can use that in policy decisions. It also is now fully aware of the ORE encryption scheme that I mentioned before, and Bloom filters and a bunch of others. And in the near future, we're going to introduce the idea of statement mapping. And so statement mapping means you can translate your existing SQL queries without any changes into the EQL form. So if you've used SAS or less in a front-end context and translates into CSS, you can think of EQL as being like that, but for SQL. So what have we solved? Well, encryption as access control gives us a bunch of things. It's reliable and works everywhere. So once you've encrypted a value, it's denied by default. You've applied those policies. It doesn't matter if it's in the application, database, data warehouse, what have you. It's denied by default, as I said. It's identity aware. So you can actually effectively implement that idea of a principal, action, and context because you always know who the principal is. It's very high performance, much faster than other systems, other encryption systems. And best of all, SQL still works properly, although that wouldn't affect you if you're using MongoDB, of course. So that's it. A little bit of information about us. You can check us out on our GitHub. Feel free to connect with me on LinkedIn or send me an email if you ever want to have a chat. We have a booth in the main hall, and we'll be here all day today and tomorrow. And if you feel like having some fun, we've included a QR code there for our capture the flag. So a little hacking challenge if you want to have a crack at that. And we also have some locks over in our booth if you feel like trying some physical security, which I absolutely suck at, so I'm sure you'll do better than me. But hopefully that was interesting, and thank you very much for your time. I think we have time for some questions, do we?
Huh?
Do we have time for some questions?
Yeah, we have time for a couple of questions.
Okay, cool.
Thanks, that was super interesting. whenever I'm learning about a system like this, I'm always super interested in the disaster recovery aspect of it. So I'm super interested in like, which bit of this infrastructure would you pour a glass of water on and lose your entire company? And how do you prevent that from happening? Because you've got like a secure enclave with a master key in it. What if you lost that? What are the scary points, and how do you build redundancy into the system?
Well, I mean, if you think about redundancy for a database, obviously if you lose your database, you're screwed. So you want to have backups of the database and, you know, high availability. All of that is exactly the same, except that now you also need to think about that for your key management. So even though zero KMS is a thing, we still actually use Amazon's hardware security modules behind the scenes. And they use what's called multi-region distribution. So funnily enough, I spoke to the general manager of the Amazon Key Management Service, and he said his team spends about 3 days a year on encryption and the rest of the year on reliability and uptime. And so we just build on that. So multi-region keys means that keys are distributed into multiple regions. They've got, you know, all the backup things that you would have normally for a database. You also now have for your key management. But you're right. That is the other angle that you need to consider. And with everything, you know, you're getting better security. You also now need to think about what's the resilience of the system. So it's something we think about a lot. That's a great question. Yeah.
Any more questions? Okay.
Yeah, thank you. I enjoyed that, and I've not sort of an area I know a lot about. But so what kind of overhead are we talking about when we're talking about much more sort of like table level operations and queries?
Like a performance overhead?
Yeah.
Yeah, so we've done a bunch of benchmarks, and actually there's some benchmarks on our GitHub. But to give you a sense of it, so the ORE scheme is the slowest of the different schemes that we use. And I'm going from memory here, but the benchmarks are something in the order of, if you've got 100 million records in a table, the overhead is less than a millisecond. So it's about 700 microseconds, I think, from memory. Yeah. So it's pretty fast.
Any more questions?
Not a question, but a clarification. For the URL that Dan had up on the screen before for the EqualPy repo, it doesn't have a dash in it, but if you just go to github.com/cypherstash, you can find it there. It's a start repo.
Fixed.
All right, well, if there...
Thanks very much.
Wait.
Oh, one more at the back. Cool. Time for one more?
Great talk. I'll pretend to understand half of it and like read about it later and understand it. But I just wonder how you solve the problem of once all this cool encryption stuff happens in the back end, when you've got a user database at some big company and someone paid a little bit per hour is accessing it, and the data is already decrypted in the front end to access it. How do you combat the human reading the plain text data in the data center, even if you've done all this work in the back end?
Yeah, so we have this idea of, I guess, principle that we think about a lot. You want to do the decryption as close to the user's eyeballs as possible. So, you know, once upon a time it used to be on a disk on a server in a rack somewhere. Then it was in the application. Now it's in, you know, transit, and eventually in the browser on mobile device. And actually, doing the decryption here is the best place to do it. And we're not quite there yet, but that's what we're working towards. That minimizes the likelihood that anybody else you don't want to be able to see the data is ever going to see it. The cool thing about what we're doing with EqualPy is we're now doing that in the application layer instead of the database. So we're kind of lifting it up, you know, further and further and closer to the user's eyeballs. But I guess there's sort of a philosophical question then, like once somebody has read a value, like it's gone into their brain until we can, I hope we never are able to do this, but we can't delete something from somebody's brain memory yet. So that's it. Once they've seen the data, they've seen the data. So by giving somebody access to the information, you're assuming that you are happy for them to have that access forever, assuming they can remember it. So there's sort of some philosophical things there, but getting it as close to the user's eyeballs as possible is how we think about it.
All right. Well, as a token of appreciation for speaking at 2024's PyCon, I'd like to present you with the speaker mug.
Thank you very much. I treasure it always. Cool.